Okay, so last time out, we just looked conceptually at how we're going to go about comparing two different methods of searching for chunks within our text. And we went through a little bit of the theory of how we're going to do that. And essentially, we decided, well, what we're going to do is we're going to take all of these text chunks and we're going to generate some questions from each of those text chunks. And we're then going to ask a particular model, hey, can you find for me the most appropriate text chunk for this question? And so because we know now the actual text chunk that was used to generate the question, we know what the right answers should be. So essentially, we can then test these models and see how well they've done on this particular task. And that is kind of a pseudo problem that we are generating to see how well these models are working. So we went through the theory of that. Now we're going to see how it's done in practice, and you're going to see that it's quite a simple process. So let's zoom into the code, and all of this hard work and heavy lifting is going to be done then by this function, generate QA embedding pairs from llama index. And you see, all we're going to do is we're going to pass in to this function the list of nodes, the list of text chunks, the llama index text chunks that we previously generated, and a large language model. And of course we need the large language model because we're generating these questions. We're going to go out to the large language model and we're going to say, hey, look, here is some text, but write me some questions that can be answered by this text. So all that is going to be going on underneath the hood. That I have already done. And eventually we get to this embedding QA fine-tuned data set out of this function. I'm just going to load this up from file because I've previously done it, and we're going out to a large language model. It's going to take some time. It's going to cost some tokens potentially. So let's get this data set, okay? And we're going to be working with this train data set. So what does this data set look like? Well, it's got queries. Now these are going to be the questions that's generated by the large language model. It's got this corpus. This is going to be the text chunks. And it's got these relevant documents. And this is what is going to enable us to get out the correct answer. It's going to show us the relationship between the questions and the text corpus. So I'll just show you what I mean. Let's just have a look at these queries. And you see with these queries, we are going to have all of our different questions. Okay, but if we actually look at those query objects, you'll see what it is. It's each question which has been generated by the large language model has got a unique identifier, and this is basically in some sort of dictionary. And so we've got lots of questions with unique identifiers. So let's get rid of that. When we look at the corpus, which is the text chunks, we've got a similar situation. So we've got some sort of dictionary here where we've got a unique ID as it relates to some form of text chunk from our documents. So now what we can do, let's just run this here. We've got all of the keys for the text chunks, and we run this. We can get the actual text chunks. We can recover the text chunks, but here we can see this relevant documents field. And what we do here is we give the identifiers for the questions, and we look in the relevant documents, and that gives us the identifier for the corpus, for the text chunk from where it came. So we can use this relevant documents to find the relationship between the questions and the text chunks. So there you go. This is just a little explanation then of the mean reciprocal rank, which is the particular metric that's going to be used for algorithms that generate, that give ranks to things. So that's what we basically get from an embedding model. It's just a list of documents which are the most appropriate. So we can think of that as some sort of ranking system, and it's ranking these documents in order for some given query. So we went through that. We're basically going to use the inverse rank of the ground truth. So if, for example, our model finds the correct document in its third item on the list, and then it gets a score of 1/3, and we take the average of all of these. So we've got some embedding model here, which was the Hugging Face model that we downloaded, the AAI BGE embedding model. And so here we can, just like we've done in previous videos, we create some sort of vector store index. And I'm still running on the CPU, so this is going to take a little time to generate, but we can carry on. Now, that is what we're going to compare, and we're going to compare against this Elasticsearch, which is going to rely on this BM25 algorithm, and I'll let you go away and research that if you want to. So we're going to pull from Llama Index an instance of this retriever. So we're going to end up with two different methods of searching this vector store. We've got the first one, which is the embedding model, and the second one, which is basically we pull out all of the documents and we use this algorithm, this BM25, to find the nearest one. So we've got two different methods of searching our text chunks to find the most relevant. And so we can run that. We're still waiting for our notebook to catch up with us here, but we can continue. And there we go. So in order to calculate this mean reciprocal rank, then I'm going to do a little play around with all of these things that we get from our data set, and I'm going to manually calculate this mean reciprocal rank. I'm not going to go through that in any sort of detail. Also, you can imagine in Llama Index and LangChain, there's lots of methods available for you to make these evaluations without doing the hard work. And there we go. Once we've done all that, we've had the large language model create all of those questions, and it's going to be as simple now as just putting in the particular retriever that's going to retrieve the documents and giving it the data, and then we're going to get some sort of score which is generated by that metric which I've explained to you. So we'll have a look at these results finally when this notebook catches up with us. I still imagine it's still creating this using the embedding model to create these text embeddings. So once we've got through that, I think we'll move forward pretty fast. But while we're waiting for that to happen, let's just have a look at another concept that enables us to take a number of different retrievers and combine them together. So in this case, we can, instead of using one, the vector retriever, or the other, which was the Elasticsearch, we can actually define a retriever. Here it's called Query Fusion Retriever. In LangChain, it is, I believe, called a hybrid retriever. And we give it both of these retrievers, and we say how many documents we want returned, and we will get documents back from both of the retrievers. And then what will happen is we will use some form of algorithm to re-rank all of those documents. It's going to look at those documents and it's going to examine those results, and it is going to It is going to give a final verdict then on which are the best documents. And so I'll put a link in the bottom. The particular algorithm which is used for re-ranking it works very well when there is a large number of different models. What tends to happen with it when we just have a couple of models is we'll have one model and we can see that the code cells have finished running, so we can go and look at the results. You see that in this case, this Elasticsearch was much better. It got 0.77, and if you imagine that the ideal score would be 1, that's where the ground truth text chunk was found in the first place in the list every time. And you imagine if it was found second in the list every time, we get a score of 0.5. So we can see 0.77. We're kind of getting, it's kind of alternating between either being top of the list or being second on the list. So that's actually a very good score. We've got a worse score here using the dense vector embedding model. And so what you'll find happens with this algorithm here is that it starts relying too much on a weaker model. We got quite a big difference between the models here. We maybe want some information from this model, but not a whole lot. But you'll find it gives too much relevance to this weaker model. When there's just two models, that goes against the final results. And you can see that if we actually run this query fusion retriever now, and we get the results, we're going to find that the results are not going to be as good as our best model. We can start to define weights, and there are other strategies we can use to make this work better. I just want to show you in this video that it is available. We can combine different models, but like I say, look at the link for this paper. You're going to have to be a little bit cute about exactly how you do it, because you'll see that the mean reciprocal rank we got here of 0.74 is actually less than our best model. And what we actually wanted to do was get the best of both models and actually improve on the best model. So there you go. That's an important concept to cover now as we start looking how we can optimize this particular workflow, this RAG workflow. And like I say, one of the crucial things you're going to want to target is which embedding model you use. And in this video, we have seen how we can start to compare the results from these different embedding models. So I'll see you guys in the next video.